Let us now examine in detail why we can make the simple 1 out of 2 oblivious transfer protocol correct. Remember that the key point that we need is that the strings x theta 0 and x theta 1 were of sufficient length. From the first two steps of the protocol, we see that the length of these strings is determined by how often Alice measured in the standard and how often she measured in the Hadamard basis. How often she measures in the standard basis determines the length of x theta 0, and how often she measured Hadamard the length of x theta 1. Let's just consider here how often she measured in the Hadamard basis. It would be the same if we asked how often she measured in the standard basis. First, let's decide what it means to be too short. Here, let's just pick a fraction, say a quarter. If Alice measured fewer than n over 4 times in the Hadamard basis, then we'll call x theta 1 too short. What we will do is that we will let Alice pad the string x theta 1 with some random bits, so it has always length at least n over 4. So if this is x theta 1, for example, it could happen that it's only consisting of 1 bit, then Alice will add some random bits. Of course, we now have to ask ourselves how this would affect our protocol. Remember that what Alice does, she computes the key k1, Alice, by applying the extractor function to the string, in this case, in fact, 1 followed by the random bits. And the seed y1. Bob does a similar computation, 1 and y1. So will the protocol still be secure? Note that Alice still receives no information from Bob. Bob certainly knows nothing about these fresh random bits, so it certainly cannot give him an advantage. Will the protocol still be correct, however? Surely the protocol will not always be correct now. Bob does not know these extra bits. So if he later applies the extractor function, he will very likely not get the correct key. The key of Alice will be different than the one from Bob. And not knowing the key does not allow him to recover the desired string from the message. Our goal will thus be to show that the protocol is epsilon correct for some fixed parameter epsilon that we choose. In particular, in order to achieve this, we need to show that the probability that the string is actually too short, in this example, meaning it has less than n over 4 bits, that is very small, in particular, smaller than epsilon. So how can we do that? First, let's define a random variable that counts how often Alice measured in the Hadamard basis. Let me call it S. S counts the number of times Alice measured Hadamard. We'll define it as the sum of random variables theta j, which correspond to the basis choice. And remember that theta being 1 was Hadamard, and theta being 0 was standard. So indeed, S gives us the number of times Alice measures in the Hadamard basis. We will now apply a concentration inequality known as the Hoeffding inequality. Intuitively, it says that the probability that our random variable S differs significantly from its expected value, ES, decreases exponentially with n. So what is the expected value here? Remember from your probability classes that the expectation is linear. So the expectation of S is just the sum of the expectations of the theta j. Since Alice chooses theta 1, the Hadamard basis, with probability half, and theta 0, the standard basis, also with probability half, this expectation value is just a half for one of these terms. So if we sum them all up, we get n over 2. So let's see how we can use this inequality. Note that here theta is in this interval, so I've already applied this to the writing the Hoeffding inequality in this form. In the example, we picked a threshold, namely our desired threshold was a quarter. So let me use here indeed t to be a quarter, and remember the expectation is n over 2. So shuffling s to the right and subtracting n over 4 from both sides, we will get this bound. So what do we have to do in order to make the protocol epsilon correct for some desired epsilon? So we want this term here to be less than epsilon. So how did I get this term here? Let's remember that t is a quarter, so t squared is 1 over 4 squared, 1 over 16. We have the 2 in front, so 2 times t squared gives me 1 on 8. So let's see what we need to do in order to make this less than epsilon. So here I've just written that we want this to be less than epsilon. So let me take the logarithm on both sides. I have n over 8 less than ln epsilon. Multiplying by minus 1 gives me n over 8 minus ln epsilon, and it will be convenient to write this as ln 1 on epsilon. So note that what I can do now is I can bring 8 to the other side. So I have 8 times ln 1 on epsilon. So this means that if we want our protocol to be epsilon secure, then the number of qubits that we send needs to be at least this large.